When we study electric forces and fields, typically we start by studying point charges. Imagine I had a charge at point N down here, and I wanted to know what electric field it created at point P up here. To find that answer, what I would do would be to use Coulomb's law. Coulomb's law for point charges tells me that the electric field at some measurement point P is equal to the constant 1 over 4 pi epsilon naught. That's got value of, that combination has the value of about 9 times 10 to the 9th Newton meter squared per Coulomb squared, times the charge of the source charge, divided by the distance between your measurement point and the source charge, squared, just divided by the distance squared, and then you multiply by r hat, the unit vector pointing from the source charge toward the measurement point. That's what we do for individual points, individual point charges. But in many situations, we have continuously spread charges over, for example, a whole line. I'm going to, in this example, talk about a charge continuously spread from one end to the other of this 100 centimeter line that I've drawn at the bottom of the board here. And I want to know what is the electric field measured at point P up here above that line. Well, that's complicated because Coulomb's law only tells us individual points. And the ideal way to solve this kind of problem is using calculus, integrating over the source charges. But to get an idea of why calculus is the way to do that, I'm going to do this example where I break this 100 centimeter line up into 10 equal 10 centimeter chunks, and I'm assuming that that charge, I'm going to say this line is a total charge of 70 nanocoulombs spread along it. And so I'm going to assume that that 70 nanocoulombs is spread evenly through this whole thing. So I guess each one of these 10 segments would have 10 nanocoulombs of charge on it. And as a first approximation to the effect of this line of charge at point P, I'm going to just treat each one of these 10 segments as if it was a point at its own center. This is obviously a very rough model because we know that really the charge is continuously spread. It's not just 10 dots, it's spread continuously over this whole thing. But this model is going to come, we'll find, surprisingly close to getting the true answer to this problem for this continuous charge distribution. I hope that by doing this, it'll give you an idea of how calculus works, how the calculus approach to this problem works, so we can talk about that later on. So to set up this problem, though, to set up this idea, what I need to do is use Coulomb's law now for each of the 10 point charges that I'm imagining, one at the center of each of these 10 segments that I've drawn. I'm breaking this into these 10 segments, and I'm imagining all the charge of each one is centered on each one, and so I just need to use Coulomb's law 10 times. Well, how do I do that? I guess the thing I need to know to use Coulomb's law, I need to know the charge on each point. We just said that. It's the total charge divided by the number of segments I've done. So each one is going to have 7 nanocoulombs of charge. I need to know the distance from each one of these source points to my point P. And so that's the first thing I'm going to do. I'm going to fill out this table, filling out the distance to point P from point I equals 1, I equals 2, I equals 3. I guess I should say segment I here to be clear. Counting along, I'm going to do it for the first 5, and then I'm going to fake it in the interest of time. So I'll do that, and then I'll calculate using Coulomb's law. I'll find the magnitude of the electric field. Basically, I'm just going to leave out the r hat because that's the direction part. The rest is the magnitude. Q is positive, so I don't need to worry about minus signs. And then I'm defining a scale. Since I'm going to draw electric field vectors on the board as arrows, I'm defining a scale where if I get an electric field of 100 newtons per coulomb, I will draw that as an arrow 1 centimeter long. 500 newtons per coulomb will be a 5 centimeter arrow, and so forth. That's the plan I have. All right, so step 1 is to fill out this table to find those distances. Let's do it. I have a meter stick here. I'm just going to go and measure from each point, each one of these 10 point charges that I'm imagining I have down here now, dividing this into 10 segments. The center of each segment is its point charge, and I'm going to measure those distances. So bear with me. This will take a minute. This is a very tedious process, but I want you to see it. I want you to understand it. Make sure you understand how this is working, why this is giving a good approximation to what's going on. So let me do this. here we go. From point 1, well done, well done. From point 1 to point P, here's this. I am getting a distance of, I would say, 52.2 centimeters. I'll put that here. 52.2 centimeters there. From point 2 to point P, I'm going to measure a distance. See if I can get this right. Distance from point 2 to point P looks like it's 43.6 centimeters. 43.6 centimeters. From point 3 to point P, where are we? Point 3 to point P should be 35.4 centimeters. This is more precision than I really deserve for this problem because my dot is like half a centimeter wide. But I'm trying to do the best estimate I can. You know, it's probably uncertainty of plus or minus 3 millimeters in each one of these or something, probably more than that. But yeah, plus or minus 5 millimeters in each one, maybe even more. I don't know. But let's see. This is 29.2. 29.2 centimeters, and point 5 to point P, that distance looks like it is 25.3, I think. 25.3 centimeters. Now, I should keep going, 6, 7, 8, 9, 10. I almost don't want to. It should be the same distances because this point P I've chosen is directly above the center of this rod. That's what I chose. And I chose it to be 25 centimeters up. I think I said it already, but in case I didn't, that distance from P to the nearest point, I call this N because it's the nearest point on this line of charge to point P, that distance is 25 centimeters. And yeah, maybe I don't want to know. Maybe I don't want to know. If I have it wrong, let me see. This I'm getting 25.3-ish. Yeah. This one I'm going to get, so 5 and also 6. 7.7 to here. I'm going to say 28.6. Oh, wow. Really? That's very different. Yeah, I'm getting 28.7, but still, 28.7. I'm going to average the two. 28.7 to 29.2, 6 to 2, 29, 28.9 or so. So I'm going to make that 28.9, roughly, as my average of the two. 4 and 7. 5 and 8. Hope this isn't too bad. Let's see where we are here. 5 and 8. I'm getting 34.9. 34.9, well, that's interesting. 35.4, 34.9. This is consistently off, isn't it? 34.9, call it 35.2 or something. That's going to be roughly right. 0.2, so that is 3 and 8, 2 and 9. If I look at 0.9, what's my distance here? I'm getting 42.8. Wow, really? 42.8. Gonna be 43.2 will be my average. Again, I'm just averaging to get rid of my errors a little bit, to reduce my errors a little bit. You can see what's going on here. 51.2. Oh, see, off by a half. So 51.7 will be my average. 51.7. Okay, so obviously in a perfect world, those would have been exactly the same numbers every time on each side. It wasn't quite. That probably means that I wasn't quite centered or something when I do that point P. I'll use the averages. It'll probably be okay. We'll see where it takes us. So, okay, with this is a point where now I want you to go through. I'm going to give you a minute. I want you to pause this video and go through and do these calculations to find the electric field for each one of these. Remember that 1/4 pi epsilon naught like I said, that constant in Coulomb's law is going to be, we don't need it very precise. We can do it's about 9 times 10 to the 9th Newton meter squared per Coulomb squared. That's our 1/4 pi epsilon naught factor. Q, the charge, is the charge on each one of these separate pieces. So for us, that Q, I could say Q sub I, the ith Q, is going to be total charge divided by 10, divided by our 10 segments. And so as I said before, that is 7 nanocoulombs, 7.00 even. So we know what that number is. And the distances here, don't forget to convert to meters. So 0.25, 0.51, convert to meters. And ignore the r hat. Take a minute and do that. I suppose I should, I pre-calculated this for the true answers, but I can see how close I came to those. Just to compare to what I'd gotten earlier. 1.5, 43.0. These are not bad for what I expected to get. These are pretty close. Yeah. You're going to get slightly different numbers. You're going to do it at home. I'm not going to take the time right now to calculate with these. I went through with what I expected the answer to be for each one of these if I had drawn it perfectly. You can use the Pythagorean Theorem, right, to find, if I really wanted to know this distance right here, I could easily use the Pythagorean Theorem. Oh, hey, whoops. Oh, I can see it's kind of tilted right there. Yeah, anyway, I could say this distance is 25 centimeters, and this is 10, 20, oh, that's 25 as well. That's 10, 25 centimeters to the center of that one. And so 25 squared plus 25 squared square root would give me, for segment, it would give me a distance of 35.4, and this is 35.2. So I've pre-calculated for this. Go ahead, calculate yourself, like I said, try it out, and we can do this. When I get these answers, let me go ahead and just write down what I find for all these things. I get 237.5 newtons per coulomb for segment 1 and for segment 10. For segment 2, I get 340.2 newtons per coulomb. For segment 3, I get 503.4 newtons per coulomb. Segment 4, I find 740.4. You know what? I should not use the decimal places because I'm already off in the 3rd decimal place here. The 4th is ridiculous. I'm going to just ignore those completely. Round this to 238 because you round to the nearest even number if it's a 5. 238. And segment 5, I get 968 as my number of newtons per coulomb. So scaled to centimeters then, 100 newtons per coulomb going to 1 centimeter, and rounding off to the nearest millimeter, because I can't do better than that with drawing on a board or something. This will be about 2.4 centimeters, 3.4 centimeters, 5.0 centimeters, 7.4, and 9.7 centimeters. That is my scaled value. This is the real value, obviously, but if we're going to draw arrows, I want these scaled arrows. Boy, all those lines are short enough. I don't want to use my giant meter stick. Let me grab a ruler really quick. One ruler I can use. And here, oh no, I do need my meter stick. Never mind. When I'm going to do this, what I want to do to take care of the r hat, rather than doing math for the r hat, I'm just going to keep track of the direction. What I'm going to do, I'm going to line up from the center of segment 1 to point P. I'm going to line up along there, try to get those aligned. I'll put this in the middle there. Okay, so those are lined up. My r hat direction then points along the ruler, and all I have to do is go 2.4 centimeters over. So I'm going to start from my point in the middle here. I'm going to go 1, 2.4. There we go. That is my electric field due to point 1. E1, I could call it. It's a vector, it points that way, and it's to scale. We've defined the scale. For point 2, I want 3.4 centimeters, and I'm going to do the same thing. I'm going to line up my point here. I'm going to line up there. This is going to be pretty flat. Point 2, okay, that's pretty good. And I want 3.4 centimeters. So let's do this. Okay, you can see that this one is a little longer and it's tilted up a tiny bit compared to E1. Hard to tell because they're both short and they're both right on top of each other. E3, for point 3, 5 centimeters. And again, I want it to be along this direction from 3 toward P. And so I line it up. Can I get a 40 lined up there nicely? Maybe. Okay. So I've lined it up. My r hat direction points that way along the ruler. So I want to go 5 centimeters. There we go. That one is E3. And you can see it's a little longer and a little tilted up. Tilted up because of the direction. It's longer because the point is closer. Point 3 is closer than point 2. So it's a longer arrow because Coulomb's law says the electric field gets stronger when you get closer. Point 4. Do this again. Point 4. There's 30. I'll line it up there. How low do I go? 7.4 for this? Okay, line it up. .4, there we go. There's my E4 vector. And finally E5. Gonna look pretty similar. Want to start it here. Want to go that direction. All right, so drawing this here, 9.7. Oh, okay. Please tell me I'm not smearing my things. Okay, that is E5. You can see how this is working. I'm just drawing all these electric field vectors in. It's getting kind of repetitive, but I'm figuring out what arrow to draw. It's not bad. I just keep going. This is, I've said before, this is extraordinarily tedious. This is not the way you would ever want to do this for real, but I think it is really instructive to at least once in your life go through and do this calculation. Do one of these. This is again 9.7 centimeters. Okay, that is my E6 vector. And then I keep going. It is tedious. I think it's worth doing this on your own paper sometime. I'm going to assign a similar problem in my class because, like I said, really, really worth doing at least once to see how these come together. Okay, 7.4 centimeters for this one. There we go. That's E7. E8. Hey, I've got a line already right here. That's handy. All right, E8 is going to be this direction and 5 centimeters long. Draw that. Again, this is so repetitive. You can see the symmetry showing up, right? You can see E8, missed that, E8. You can see that each one is reflected across. That's because this is above the center. If it weren't perfectly centered, it wouldn't be quite like this. But each one has a pair on the other side, a partner on the other side, that's basically the same length as I go. Okay, we're almost there. Let's see, is that, how far are we going? 3.4 centimeters? Tell you what, I'm just going to start here at 47. Okay, and sometimes getting a ruler to work on a board is a pain. But okay, got this. 3.4 centimeters. It's going to be 3.4-ish is there. So there we go. That's my E9. And one more. Last one. This is tedious. Now, you're saying, why am I doing this? What is this for? Okay, that's probably just a general thing you're saying. I'm supposed to go 2.4 centimeters. I'll start at 54 here just so I can line it up. 2.4 centimeters from there is going to go 2.4. it looks a lot like the other side, doesn't it? E10 over there. You can see now this perfect symmetry going back and forth, where at least pretty close to perfect, going back and forth like this. So why did we do this? I've now drawn the lengths with my scaled length here. These lengths represent newtons per coulomb, hundreds of newtons per coulomb. I've drawn these lengths. I've gotten the directions right, not by doing some complicated r hat calculation, but just by following lines, right? That's what r hat is. It's just from there to there. That's what r hat means. It's just that direction. So I've done all this. I've calculated those. Now what I'm supposed to do is find the total electric field. How do you find a total electric field? Well, you add. I just take these arrows and I add them together. Tip to tail, tip to tail. I'm going to start with the longest ones first. And maybe what I'll do, I've got E6, which is going to go to here. I'm going to add E5 to it. Let me try to do that by putting a parallel line like this. I'm going to try to make this parallel to E5. How long is E5 again? Yeah, it's 9.7 centimeters long. So where can I start this? I'm just going to go here. What I'm doing, I'm trying to line up the ruler to be parallel with E5, but I'm going to start it at the tip of E6 because I'm adding vectors tip to tail. That's how we add vectors, tip to tail. So I'm going to go my 9.7 centimeters from here. 9.7 to there. Cool. So that was E5 that I just added to E6, right? Vector sum, starting from my point, E6 plus E5, tip to tail. So I've done that one. Let me add E7. I'll do that one next. Again, I want to draw a line parallel to vector E7. I want that to be this direction. And it's going to be tip to tail with that. E7 has length 7.4 centimeters. I've come up to here. Let's go 7.4. Obviously, this is really rough. This is not a perfect drawing. So this is E7. I'll sort of check it off down here when I do it. I'll do E4 next. Again, I'm going longest to shortest just to get the long ones taken care of. E4, again, I'm going to do the same thing. I'm going to line this up to be that same direction as best I can. And then I'm just going to smoothly slide it over. That looks parallel. Smoothly slide it over in that direction. Okay, and there's my tip. And I need to go, for E4, I need to go 7.4 centimeters again. So to there-ish? Not quite to there. Okay, that's pretty good. That's pretty good. That is E4. Check it off. Just sort of mark it that I did it. Okay, you can see where this is going. Next, E8 is this one. Okay, well, E8 is going to be 5 centimeters long, and it's in this direction. Go parallel to that as best I can, and then I'm just going to slide it upward parallel to that as best I can, kind of, maybe. Again, you could do better than this if you want to be really careful, but if you want to be careful, use calculus. 5 centimeters. All right, that was E8. You can see what I'm doing. I'm just adding up, tip to tail, the electric fields due to each one of these. Next is E3, I guess. Coming this way, same deal. E3 is here. Let me get ready to, I want to go parallel to E3. I don't want to screw up the direction. So I'm going to slide this upward as best I can. Okay, maybe. And I want to go, again, E3 is 5 centimeters in this direction. Hopefully I can hold this steady enough. There we go. That's my E3. Something to notice as we go along is that these are getting flatter and flatter, and as they get flatter, they get closer and closer to canceling each other out. I've done E3. E9. This gets tedious. I told you it was tedious. I hope you believed me. You do now, if you didn't before. Okay. I'm going to slide this straight up once I get parallel to E9. So E9 is pretty flat. It's kind of like this. Okay. Kind of like this. Let's do it, E9. Something like this, I hope. And E9 is 3.4 centimeters long. We'll do it. So slow. This is hopefully illustrating why something like calculus is a good idea, because it takes care of these things for us. E2 will be next, and it'll also be 3.4 centimeters long. E2, line up with E2, not E3. Get the direction right. Get the direction right. Okay, well, here we go. I'm just copying these up, right? That's how we do vectors. We do vectors by just copying them. We keep the direction and the distance the same, but we can move them around. Keep that going, 3.4 centimeters. Okay, that was too far over. Went to here. That was E2. Mark it off. These last couple, okay, where are we? Where are we? This direction. Let's do it. Yeah, this direction. And how far in this direction? 2.4 centimeters. 2.4. That is my E10. And the same thing for E1. Last but not least. Okay, it's pretty least too. I hate it. This is so tedious. Okay, that's about right. Get this direction about right when I bring it up. Okay, sliding it around. And again, 2.4 centimeters at this angle. About there. Okay, now, let's see what I've just done. I totally meant, if I had done this right, I would have done black last, because I have to write over all this. My overall vector for this, my overall electric field vector goes from point P straight up to the tip. It's from the initial tail to the final tip. That's my sum, my vector sum. Let me draw it in here. I'll draw it in bright color just to get this vivid for you. I'm going to draw it and then I'll measure it. So from the first tail up to the last tip, about there. Better hold this in place, otherwise it's going to slip. Okay, I actually did pretty well with this. I feel good about it. I'm about to do terrible things with this marker, though, going over all those black marker bits. All right, that vector right there is my E total. Couple things to notice about E total. First of all, it is longer than any of the individual vectors were, because we added them up and they were more or less in the same direction. They were all upward, all away from this long line of charge. That's what we expect, right? It's a positive charge, and electric fields point away from positive charges, so we expected all the vectors to point upward. That's great. Also, it is basically straight upward. I actually am pretty impressed with the degree to which my arrows canceled out left and right, because I was just drawing those kind of eyeballing it. But you can see that adding up all those arrows, it's straight up. It adds up to because I chose a point that was above the center of the line, it makes sense by symmetry that it doesn't tilt one way or the other, that it's straight up. That's a good double check. And for the strength of it, let me measure. It looks like this is about, I am getting 43.4 centimeters, which based on our scale says that the magnitude of my electric field total is about 100 times that, right? 43400. Is that right? Yeah, 2,500. Yeah. Well, no, that can't be right. Just two zeros. 4340. That's more like it. Yeah, 4,340 newtons per coulomb is what I come up with just doing this drawn picture on the board. Using these arrows to scale, I got that result. Now, I have actually done this calculation in a couple of different ways. If I do this calculation using an explicit formula for a finite line of charge with this length and this charge on it, that formula, what's it look like? I might remember E for a finite line using calculus is something like I'm not sure I'm going to remember this. I probably shouldn't be quoting this off the top of my head. 1 over 4 pi epsilon naught times q over the distance of the point from point P to that nearest point down there times the square root of the length over 2 squared plus that distance squared. It's something like that. I should probably have had this in front of me before I tried to write it on the board. I wasn't planning on writing this bit, but it's something like that. Double check it. If I do that for our case, then the magnitude, well, this is the magnitude part, and I should say absolute value of q. The magnitude I came up with doing this finite line calculation was, let's see, 4503 newtons per Coulomb. So honestly, given that I did all this by eye and was just measuring things and all that, this is surprisingly not bad for having just drawn things on the board, having just done this. Now, this is for a case drawing this for a finite line. Double check that formula. That may not be the right formula, but for a finite line, it's something like that. This is a harder formula to come up with. It's actually kind of nice. There is a formula for an infinite line of charge. If you have an infinite line, for an infinite line of charge, that magnitude is 1 over 4 pi epsilon naught times 2 lambda over that distance r pn, and just over the distance, where lambda is q over L. And so you can see these formulas are pretty similar, right? If I put q over L in here, it's 2q over r times L, or r times L as a denominator, and this is the r, and that's something like L. So it's similar. It's similar, and the 2 here, yeah, you can go through a bunch of stuff. But the point is, as we do this, if you plug in these numbers for an infinite line of charge, this is a formula that you probably should know, that's useful to know in a class on electric fields and things. For this infinite line of charge, you would get, what is it, 4480 or so, about 4,480 newtons per Coulomb. Wait, is that? That's not what I meant to write. No, that's not the right answer at all. Looking in the wrong place. Looking in the wrong place in my notes. Infinite line, 5034. That's what I meant to write down. 5034. 5,034 newtons per Coulomb. If you plug in the numbers for this one, why is that one so much bigger? Well, that would be if this line extended out to infinity with the same 7 nanocoulombs in each 10 centimeter segment, but out to infinity. So there would be a lot more charge in the universe. But it gets farther and farther away, so it doesn't make a big difference because it gets so far away. That's why this is not that much bigger than the results we got either breaking up into pieces or with these things. Now, the best way of doing it is this one. And you would have to use some calculus to get there. Maybe you'll learn about it in the book or in your class or something, how to use calculus to find this answer. This is the best answer, but this one, where we broke it up into just 10 pieces, isn't bad. And maybe the thing I want to say about that is, the whole idea of calculus is that, well, breaking this up into 10 pieces came up with a pretty good estimate for doing 10 pieces. If instead of breaking up into 10 centimeter segments, if I had broken this up into 1 centimeter segments, 100 1 centimeter segments, I did too many lines there, didn't I? If I broke it up into 100 1 centimeter segments and did that, this number would have been even closer to this one. It would have been even more tedious. It would have been awful. If I had broken it up into 1,000,000 segments, this number would be almost indistinguishable from this one. That's literally what calculus is. Calculus is the process of taking a continuous spread of charge, a continuous function, a continuous something, breaking it up into tiny little pieces, and adding up all the little pieces. That is what calculus is all about. Calculus is about taking something, breaking it up into little pieces, and taking the limit as those pieces get infinitely small. And so that's why the calculus version is so much such an efficient way to do this and gives the right answer efficiently, it's because you're breaking it up into infinitely many pieces instead of just 10 or 100 or whatever. You're breaking up into infinitely many pieces. And then the great thing about calculus is we've got these cool tricks like integrals that let us do all of those calculations at once together rather than having to make a table with 100 entries or 1,000,000 entries or whatever it is. Calculus is great for saving work because there are these great tricks that let us do all of those at once together. It's kind of a mess, but that's what calculus is for. So this is just an example of how you can do the poor man's calculus, the not doing calculus but using the concept of breaking things up into pieces. To do this calculation, find the electric field of a line of charge and come not bad, come pretty close just by drawing pictures. I hope this is giving you some insight into how breaking up things into pieces, breaking a continuous thing into pieces, can give you a decent approximation into how r hat works, the r hat being all those directions, into how, and hopefully this will lead into the way that calculus then can automate all this for us and make it easier. So, all right, that's it for today, and I hope that was useful.